So let's continue our discussion of linear programming. So again, the geometric perspective of linear programming is helpful because it helps you interpret what this sort of algebraic formulation is saying in a way that allows you to realize, in some sense, what kind of constraints really matter, what don't, and how to interpret them. And so hopefully, in the future, when you think of linear programming, a picture you should always have in your head is something that looks like this. Right, with the idea being that there's some polytope of feasible points that satisfy all the constraints you want your problem to solve, and your goal is to optimize, and the optimization function is a linear function that pushes you towards one edge of the polytope. And there's some vertex there that's your answer. So the whole problem of doing linear programming, of writing optimization, is the problem of finding that extreme point along a particular direction. Okay? And that's a picture you want to keep in your head in general with linear programming. Also, there are other kinds of optimizations where the constraint, as long as the constraint polytope is linear, it'll look like that, and then you might have some other function. So we spent a lot of time in the past talking about flows and cuts, and I kept sort of alluding to the fact that these are special examples of this more general framework called linear programming. Well, now we're here in linear programming. So one thing I'd like to start with today is to show you how the things we talked about as flows can be easily put into a linear programming framework, which also means that some of the things we've worked hard to figure out, okay, what happens if you have an edge demand or a vertex demand or things like that, those are very easily addressed in a general framework. In the language of flows, we need to work very hard to translate things. In the language of linear programming, it becomes obvious that these things are all part of the same problem. And so the first exercise we're going to do then is to figure out how to write a flow problem in the language, which is an optimization, maximize the flow, in the language of linear programming. Okay? So as always, we have variables, we have an objective, and we have constraints. Right? So if we want to express a flow problem, a max flow problem in a graph, a directed graph and ST max flow, in the language of optimization, or the language of linear programming, which is a specific kind, what are the variables we need? What are the variables? What variables are we trying to, instantiate? We're searching over the space of some things. That's my variables. And then we have constraints on variables. What are the variables?
One variable for each edge showing the flow through that edge.
Okay, we want one variable for each edge showing the flow through the edge. Why? Because, well, we're searching for a flow. So the thing we're searching for is a flow. Flow is assigned to an edge, so we need one variable per. So we have one variable, xe, which is the flow on edge. Okay. Are there any constraints on this variable initially, without looking at the graph itself? Are there just any medium constraints you might have on this variable? Well, we want the flow to be non-zero. I mean, to be non-negative. Right? So we might say something like xe greater than equal to 0. Okay. Are there any other variables we need? Is there any unknowns in our situation? In other words, once we have these variables, can we write down the objective? Is that easy? Okay, what is the objective here? Again, assume we have a graph, we have a source, we have sink, we have edges, we have all the usual stuff. So what is the objective function? What is the thing we're trying to optimize? We're solving max flow, right? So what's the thing we're optimizing? Not a trick question. What is the thing we're optimizing when we're solving a max flow problem? We're optimizing. Sorry? Over which edges? So can you be more specific? We have to write this down, right? I can't use words here. What do I say? So come on, keep going. Flow over the source. So how do you say? How do we write that in this language? The only language we have is the language of these variables. So what do you want to say?
That's a max of sigma sum of x is.
Yeah. Over what? Your summing over what? Well, you're summing over. There's a summation, right? You're summing a bunch of things.
Of edges.
Which edges?
In between the sources.
Are there edges between the source and the sink? There may be no edge between the source and the sink.
Maximize the flow coming out of the source. That's it.
So how do I end that?
So sigma of x e, where e belongs to edges coming out of the source, and minus flow which is coming into the sources.
Okay, but yeah, sure. Right. Okay, sure. Oh, this is the net flow going out of the source. Yeah? So you see what we did? We took the variables. We expressed our objective in that language. Okay, what are the constraints? What is an example? What is the constraint we want next? I mean, at this point, I can put xe equal to 1 gazillion on every edge. I have maximized my flow. My flow polytope looks like this. There's an x greater than or equal to 0 constraint, and I can go as far as I want. But
the xe is less than the capacity.
okay, good. So for all e, xe is less than or equal to ce. So my new solution is I'm going to put a flow of ce on every edge. This problem is trivial to solve. I've just done it. I put ce on every edge. That's the only constraint that I'm required to satisfy. I'm done. Are we good? No?
The amount of ingoing should be equal to outgoing. I mean, the flow that is ingoing.
Very good.
Yeah. So sum of xe over when e is suppose we are going to vertex v.
So fix the vertex v.
Yeah.
This is true for all vertices v.
Yeah.
Okay. So for all v not equal to source or sink, okay, what do we do?
So from all the edges that are going inside v. So sum of xe where e is all the edges which go to v.
E is of the form. What must E look like? Look at the example we have.
X.
Well, I don't know. What do you want to say? What are you trying to say?
I want all the edges that can go inside v.
So what does that edge look like? If there is an edge that goes to V, what does that edge look like? How do you describe it? An edge is two parts, right?
Yeah.
So how do you describe it? No. How do you describe it in algebra? No. Yeah, it's not
I mean, I'm
Think.
thinking.
Yeah. An edge that goes into V is of the form.
U comma some edge, some
Okay,
vertex
some,
U
yeah.
comma vertex.
Alright, yeah.
Okay.
Should be equal to sum of all the edges xe, where e is again from v to w.
Good. We've now expressed the conservation constraint. That was first was the capacity constraint. This is the conservation constraint. These are legal constraints in our language of linear programming. This is an equality, but we know that equalities can be handled with inequalities. So you write this as two copies. That's fine. This is a valid constraint. And this is a valid objective, which is linear, right? It's a linear function of the variables, and those are variables. Is there anything else we need to? Are we missing anything? If this is our flow polytope, will every point that satisfies these conditions be a valid flow? That's what you'd ask. I'll forget the objective for a second. Does any set of values of x that satisfy these constraints, will it constitute a valid flow? Okay, not a trick question. I'm just asking. Are you convinced? There seems to be a lot of hesitation. Is no one sure of this? We've studied flows for 2 weeks or 3 weeks, right? So is there something missing here? You're all thinking there's something missing and I need to find it. I'm not saying that. Maybe it's just fine. You just have to make the argument. What are the properties of a flow that we want to satisfy? You want to satisfy that the flow doesn't violate the capacity of an edge and the flow is conserved. There's no trick question. It's fine. That's why make sure you check. So once we have this is now a linear program, right? Because it has you can write it in the form that you're maximizing an inner product. Right? You can write this as an inner product, right? Because it's coefficients here. Bus was late. You could take a note of your copy. Just me. So you can write this, because it's a linear function, you can write an appropriate C transpose X form, and you can write this in a matrix form. It takes some work, but you can write this in a matrix form. It's not too hard. If you think of a matrix as sort of a vertices down here, edges up there, it's kind of easy to write this out, but you can do it. And that's it. So we now have a flow. And we can solve this because we can solve linear programming. So in other words, in some sense, we did not have to go through all the work of looking at Ford, Fulkerson, and everything else. We could say, look, a flow is a special case of a linear program. People have figured out how to solve linear programming. It's solved. That's not wrong. Of course, there are more specific constructions for flows that make it easier. But here's one thing that's interesting. Now that I put this in an LP formulation, suppose I now say, oh no, I have this extra constraint where, let's see, every edge must have a certain amount of flow on it at demand. Otherwise, the sludge sits in the oil pipeline and it can't flow. How would you say that here? How would you express the constraint that every edge must have a certain amount of flow on it, given by some input demand on each edge, which could be 0? Okay, so now we can add in a new constraint for all E, XE greater than or equal to D, right? Edge demand. Right? Suppose we have another constraint. Oh no, we need to make sure that the amount of flow going through a vertex is not too much. Because it's a little, like joint here and it can't take too much flow. How would you express that? So that I don't have a capacity for a vertex. How would I express that constraint here? Can I express that constraint here? What would I say? How would I say that I have a limit on how much flow can go through a vertex?
The sum of the flow going into a vertex must be less than.
Good. So let's write that down. So for all V, the sum of the flow going in, and we've already written that down, so you know what that looks like. Sum of XV E is equal to U comma V is less than or equal to some capacity of V, which is given to us, right? I've just added two new things here. When we were talking about flows, we spent a lot of time thinking about how we would make that look like a flow problem. Here, in the language of linear programming, these are just more constraints. They're linear constraints. We can just throw them in, and we can still solve this using linear programming. Okay? So again, one of the points of linear programming is that it allows you to see what's really important and what's not. None of this changes now. I mean, I can just do this. In fact, if I wanted to put costs of the flow, I can put a cost function. I can say I want not just a flow, but a min cost function. It still all works. So the reason we want to look at a problem in the language of linear programming is because it allows you to see how many variations of the problem can still be solved within the same basic framework. They don't need a new idea. And if you take away anything from an algorithms class, right? I keep saying this, but this is one of the many things you should take away from an algorithms class. But one thing to take away is that the right abstraction is flexible enough that you can change the problem in many ways depending on your real-life constraints. And the core computational question will remain the same if you found the right abstraction. And for many problems, linear programming is that abstraction. That your problem might look very different, but when you put it in the right language, it all just looks like a small variation. But you wouldn't have seen that if you hadn't. The same thing is true for optimization in general, right? There's so many different problems in machine learning, but if you can put them all in a single optimization framework, then everything is just a constraint. You have a core framework, you just add constraints to it, and it doesn't make it necessarily easier or anything, but the core methodology for how you solve the problem becomes fixed. And that's a very powerful thing to have in your arsenal. Right? It's one thing to say, oh, we can put out a divide and conquer trick or a Deming program. That's fine. Those are good tricks. This is a trick on a whole other scale. where just the language itself unifies this whole bunch of different questions. Okay? I mean, in some sense, every intractable, we'll get to this in a minute, every intractable problem in sort of in computer science, at a certain level of intractability of the kinds you see, thousands and thousands of problems, can all be put in this framework with some limitation. Okay. So this was an exercise in showing you that a problem that we've studied for a while, flows, can be put in this much more general framework. And to get to cuts, we'll have to, as later on, maybe the next lecture or two, we'll see how you can get to cuts again from this general framework. Okay. So this is fine. We can express flows in terms of linear programming. I cheated a little bit because I said that, oh, it's easy to see now that all these extra constraints don't change your flow formulation. But the flow formulation had one nice feature, that your solutions were integer values. If you had integer inputs, your flows were integral. You didn't have fractional flow, you had integer flow. It was a nice property. And that property remained true if you had all these extra constraints. But here I have a linear programming problem. My values could be infinite. Right? I don't know what they're going to be. They may not be integer values. And in the case, for example, of something like a matching, where your answers are either 0 or 1, it's kind of important that you get integer values because either you're picking an edge for your matching or you're not picking an edge for your matching. So we haven't talked about this yet, right? But in the geometry of linear programming, what does it mean to say I want integer solutions? And so one way to think about this is to go back to our picture from above. Okay? And what I'm going to do now, I'm going to do something inside it. I'm going to add okay? The way to think about this integrality constraint is to say that, yes, my feasible region is at polytope, but I only want the best green point inside that polytope, not the best point. What is the, if you look at this optimization, we're trying to optimize that red point is our optimal point in the linear program. What is our best point that's also green? Well, if you look at it carefully, we have drawn it. The best point that's also green will look something like this. I have to draw it in parallel, of course, the red line. It'll be this, right? Now that point is almost on the edge of the polytope, maybe not quite. It's some point there inside. It could be on edge, it could not be. It's also not as high valued or low valued or best valued as the red point. And the red point is the extreme point you can get, the best answer. This one, a little bit less, right? So when you're trying to solve a program with integral constraints, a linear program with integer constraints, also called an integer program or integer linear program, you actually want to find the best green point, not the best red extreme point. Which means you essentially have lost geometry. You don't have that nice geometric property where you can say, okay, I will find a vertex of the polytope and that's my answer. It's gone. In a certain sense, this is why integer programming is a hard problem. It's not easy. It's not polynomial time, at least as far as we know. If integer programming is anything complete, if it were in polynomial time, then a lot of other things would be in polynomial time, including all the cryptos. Most of them. So what do we do now? We want that green point. All we can get is a red point. One option is that we get lucky. One option is that, in fact, our polytope does not look like this. Suppose our polytope instead looked like just so happen to look like this. In other words, all the vertices of the polytope happen to be on the grid. Okay? If that were the case, and we knew this, then we could pretend the grid points weren't there. We could solve the linear program, which we know how to do. And because we know that the polytope vertices are always on the grid, we know that every answer we get is on the grid and is an integer point and makes it happen. So getting lucky in this case means that the way we set up the problem, all these solutions were on the grid. And notice that the thing that describes the polytope is not the objective thing. It's just the constraints. So all we have to do is look at the constraint matrix and say, does this somehow give us the property that all the extreme points of that polytope happen to be integer points? If that's the case, then our linear program gives us the same answer as the integer program, and you can solve the linear program, which is easy, and get a solution to the integer program, which otherwise would be hard. Of course, there's no way to get lucky by design, and you're not getting lucky. But it turns out there are some very beautiful theorems that tell you under what conditions the constraints give you integer solutions. So remember, we have a constraint matrix that looks like this. We have a constraint set that looks like this. Right? It turns out that all you need, and this is an if and only if, is some nice property on this matrix here. And if you give some property to that matrix, you're guaranteed that all the extreme points, not just the one you're looking for, because there's no cost function here. I could be looking in any direction to find the optimal solution. Any extreme point to look at will be the integer point. One version of this statement is that if A, and I'll explain what this phrase means. So I'll explain what totally uninormal means, but it's already a sort of nice property that you can just look at this constraint matrix and say something about what my extreme point is going to look like just by looking at that. And I won't go into this in great detail. I will say that the property is that one version of this property is that every So if you take matrix A, every subdeterminant is take any square submatrix of any kind and look at its determinant. Okay? It should either be 0 or +1 or -1. That's a definition of totally uniform. And the claim is that if your matrix A has a property that this holds true, then all the extreme points are going to be integer points. And then you can say, if you look at the constraint matrix you get from a flow problem, it is totally uniform. And that's why you can get integer solution to this. So in other words, constraint matrix for a flow problem, or flow, is TUN, totally uniform. So if you have a problem with integer constraints, and you write down the integer programming formulation for it, and you look at your constraint matrix very carefully and design it cleverly, it turns out to have this property, then you're done. You can solve the associated linear program, get the answer, guaranteed that you have big church points. Okay? And so there are many, many problems for which, even though it looks like you have this hard integer constraint, the problem ends up being easy to solve because of this property. So just the fact that you have an integer linear program for a problem doesn't mean it's not a bad thing necessarily. But that whole space of things that can be expressed in that form have some good problems, some hard problems. Okay? And so again, I want to emphasize what's interesting about this is that all it looks at is the constraint matrix. It's not looking at the objective because it's saying, look, all the extreme points are going to be integer. I don't care what your objective is. It's a property of the pointer. And again, this is one of the things where geometric thinking sort of is coming into play. Although the proof of this is more linear. But sometimes you aren't that lucky. Sometimes you don't get a problem. And so, by the way, I should also mention that it turns out that even if you add in those extra constraints that we talked about, for having flow demand or vertex capacities, this will still be true. Which is why you will still get essentially a flow problem with integer values. Right? So you can't always get total inequality. That would be nice. In general, you might have a problem where you do require integer constraints and you can't get those. And there is this fundamental difference between the integer program and the integer program. In other words, the picture doesn't look like this. The picture looks instead like this. There is a gap. So let's take an example of such a problem. So again, we're going to take a problem. We're going to take a problem of vertex cover. I forget if you've covered vertex cover in class already. Have you? In some form?
You did it in homework.
Oh, the homework. Right? That's what I thought. I was familiar, but okay. So if you recall the vertex cover, you have a graph. And the goal is find a subset of V. Right? No. Okay. And a subset of V. Right? Such that for all vertices in V, there exists some edge adjacent to V, and the size of S is as small as possible. So for example, if I have a graph that looks like this, okay, I have 6 vertices and a possible, let's see, okay, so here's a vertex cover. Right? This one. Obviously, you can't do any better with this because you need every edge can at most hit 2 vertices. There's 6 of them, so you need at least 3 in a vertex. But that's not always a sort of good way to reason about this. Right? Just because I couldn't get 3 doesn't mean it's not optimal. So now, how do I? So I want to solve this problem using linear or integer programming. Let us try to write this as one of those things. So variables, objectives, constraints, right? So what is the variables here? So how about I give you all 5 minutes? Think about how you would write this as a linear or integer program, your choice, and we will come back in maybe 3 minutes. Again, the goal is not to solve it. The goal is to express it as a linear program. Think of your variables. Think of what your objective has to be. Think of what your constraints need. Okay. So what I'd like to know is, where are you struggling? What is difficult as you try to think through how to do this? I don't want to know the answer. So I don't want answers to the form. It was difficult and here's how I solved it. Where do you get stuck in the first place? Where's the first point you're like, okay, now what do I do? Sorry? In the constraints? So you are okay with the variables and the objective? Or did you start out with the constraints?
Like edges which belong to S.
Okay, so you were able to figure out what the variables should be. You were able to figure out how to write the objective. You were struggling to write the constraints. Okay. And can you say something more about why it's difficult to write the constraints?
So basically we need to find edges so that we cover all vertex.
Correct.
So
How to encode that idea. Okay, all right. Anyone else would like to share sort of a struggle that they were having with this?
Variable also is not that. Variable.
It's not clear. So what were your what were you trying to figure out what to do?
So the variable is basically we select the edge or not.
Right.
The binary something.
Right.
And
But is that so? Okay, that's what you did. So is that so? Are you saying it was difficult to figure? I'm trying to figure out what the difficulty was.
the difficulty was using this to write the.
Okay, so in other words, again, getting the variables wasn't hard, but then encoding the constraints appears to be the hard thing, right? Okay, so in other words, we can clearly see that since we're choosing edges, there should be a variable for edge. Since we're choosing, we have a 0, 1 constraint. Okay, so the first thing is we have one variable per edge, and it's 1 if edge is chosen. No one said anything about the objective. I assume it's easy to write out the objective. Would someone like to call out what the objective is going to be?
Minimize the size of S.
Minimize, wait, that's not in objective language. I don't know what S is. I don't know what size of S means. Is that right? The language of my linear program.
Yeah, minimize the sum of X each chosen.
So minimize the sum of X, right? It doesn't have to be over S. It's automatic, right? Because it's 0, 1. Right? Okay. And so the tricky part now, as always, is how do you write the constraints? So the constraint in English is every vertex needs to be covered. A slightly more detailed version of the constraint is I must pick at least one edge adjacent to V. Okay? In other words, in the language of the linear program, picking an edge corresponds to 1. At least one of the edges, at least one of the x's for an E around V must be 1. When you have an at least something must be 1, what is the way you could do this? So think of this like an OR, right? This is an OR constraint. One of these things must be 1. I don't care if there are more than one, but at least 1, right? It's an OR. An OR of all the binary variables there. Generally speaking, an OR, if you put it in algebra, becomes a sum. So how would you write that here? You would say something like, I want to make sure that the sum of all the edges of the form, and this is a set. So, so for all u, all edges of the form u comma e, which is a set. So there's no incoming outgoing. Xe must be chosen. Something must be chosen. So this must be greater than or equal to. Okay. Yeah? So now we have variables, we have an objective, and we have constraints. And finally, notice that our constraint, this is an integer linear program, because the thing xe should be 1 or 0. So we can say, okay, maybe we get lucky, it's one of those weird, totally dumb unit modular, something or the other, whatever, and it's going to be good for us. And the linear solution will be an integer solution. Alas, that will not be the case here. And the way you can show this is by a simple example. So the way to prove that the integer solution does not look like the linear solution is to construct an example. So let's construct an example. So we're trying to minimize, okay. So I'm going to give you a graph now. Okay, so before we do anything, let's ask ourselves, for this graph, what is the size of the minimum vertex cover? No more, unless you believe the minimum 2 and 3 is 2 or 3, 2, right? Okay, any two edges will work. Can't have one, can't have two. We're all agreed on that. Okay, good. So we'll write that down. So the vertex cover of this graph has size 2. Okay. Now let's write it in the linear form. Okay, so let's label these A, B, and C. Okay, and so now we can say there's going to be 3 variables: XAB, XBC, XAC. Right. So we want to minimize XAB plus XBC plus XAC such that XAB plus XAC is greater than or equal to 1. That's for the vertex A. XAB plus XBC is greater than or equal to 1. That's for vertex B. And XAC plus XBC is greater than or equal to 1. That's for vertex C. This is our linear program, right? So let's now drop the integer constraint. Because it's a linear program, we want to solve it. Let me solve this. Can we get a solution to this that's better than 2? What do you want? So you're claiming we should put all values to be half, right? So set okay? What happens now? Look at the first constraint. Half plus half, more than 1. Second constraint, half plus half, more than 1. Okay, that's all well and good, but what's the objective now? The objective is now half plus half plus half. 3 over 2, less than 2. If you wrote this linear program and said, hey, solve it, it will give you this solution. And now you're a little bit like, I didn't want that. Tell me which edges to pick. I don't know. Pick half of that edge. It's like, I don't want to pick half of that edge, but no, pick half of the edge. Your linear solution is not the same as your integer solution. And this is going to be true because the way we've constructed the linear program, it allows you to get slightly back. You cannot solve this problem. Which means that in general, for this problem of vertex cover, if you wrote this linear program, you cannot guarantee that you will get the integer solution, the optimal integer solution. There's a fundamental difference. And this is what is called, so we'll write here, so this is the LP star is equal to 3 over 2. The vertex cover is equal to 2. And this is what is called integrality gap. In other words, it's a limit on how much, how close, how well you can estimate the true optimal value using that linear program. Now, if I chose a different linear program, maybe I could do better. And in the world of combinatorial sort of operations research, then you can think of this way. I have a polytope. In this picture, my polytope contains points that are not integer, right? In some sense, one way to think about it is say, okay, can I add extra constraints to kind of slice off all the bits of the polytope that are non-integer, so I only get the integer points left? Sometimes you can do that. You get a different linear program, and then maybe the gap will get smaller. So there's a lot of art in how to design the right linear program that gets better and better approximation to it. But that's another story. The point I just want to make here is that you can have a situation where you have this gap. You cannot get any further. So what do? And here's another very beautiful idea that comes from the world of approximation algorithms. Even though the linear program doesn't give us an answer we can use at all, it's still, in some sense, relatively well-being, given that it satisfies all the constraints we wanted. Could we somehow mutate it, change it, to get to an integer solution? That's good. So let's go back to our picture, right? So we go back to our picture above. Here. We're in a situation now where the green one is the 2, and the red one is the 3/2. They're not the same. It's not feasible from an integer point of view. But is there a way to take that red solution and move it over to the green by changing it somehow, by observing properties of that red solution, the values we got? And this is what is called the idea of rounding. So you know what rounding means, right? You take a fraction and you just round it to the nearest integer. Here, I'm taking a point and rounding it to the nearest grid point, or some nearby grid point, maybe not to the nearest, some nearby grid point. Is there a hope that if I found the best solution that ignores the grid and change it a little bit to make it integral on the grid, that I get a solution that's decent, even if it's not best? If I can do that, then I've got the next best thing. I don't have the optimal solution. I can't solve them all at a time. But I can first solve a linear program, and then change it a little bit, and I get a solution that actually is real. So in the world of this area called approximation algorithms, this is a very, very powerful tool. Idea of LP rounding. To solve an integer programming problem, solve the associated linear programming problem, which we know can be done, and then round the solution. So let's go back to our problem here in vertex cover. What would it mean to round the solution? Here's what we're going to say. So we're going to define new variables. So set x prime e to be equal to 0 if xe is, here, less than half, and 1 if xe is greater than half. Around it, right? I now have an integer solution to this problem. But there are two things I don't know. First of all, I don't know if it's feasible. I don't know if by accidentally changing it, I've gone outside my polygon. That's one thing I don't know. The second thing I don't know is if it's an equal. So first, let's figure out if it's even feasible. In the process of doing this, have I destroyed the feasibility of my answer? What would be an example of destroying feasibility of my answer in the case of vertex cover, if I went from these values to these values? What could go wrong if I claim this was my solution? So there's a solution, right? I can actually pick edges now. There's 0 or 1. What could go wrong just from a purely feasibility point of view? Yeah?
Example, if you have 3 edges and one curve, it's still satisfy the sum equal to 1, but then xe is 0. We have 3, but that has 3 edges adjacent to it.
Okay.
And in your solution, you have each of them equal to 1 curve.
Yeah.
And it still satisfy the condition that it's bigger than 1, bigger or equal 1.
Right.
But then by definition of SE prime, one of them is 0.
So you'll never cover that vertex. So the problem with feasibility is that by doing this, it might be the case, right, that you never pick a vertex, right? That some vertex never gets picked because of the way you assign things. And so the question is, can we show that this will not happen? In other words, can we show that the x primes are sort of feasible, and then we can worry about how good this solution is. All right. Let me make sure I got this right. I can't remember. basically there's a way to show. So what I'm pondering here is that the example that you gave is a good example. If it turned out that I had say 10 edges around a vertex, and I assigned all those values to be 1 over 10, then I would never pick that vertex, even though in the linear program it satisfies the constraints. And I wouldn't want that to happen. The way that we prove that this doesn't happen is by showing that in fact you can always guarantee that some edge will be at least half. I'm trying to figure out why that's the case. Given the time, it may be that we have to adjourn now and I continue this next time. Give me 1 second, and if not, then we'll. Let's okay. Maybe I'll pause for now because so let me stop right there. Then let me just do this. So let me explain where we are so far. What we've argued is that the conversion from integer to linear sometimes will make you sacrifice the quality of the solution. There could be a gap between the best integer solution and the best linear solution. The example of vertex cover is one such example where when you write down the associated linear program, you can get answers that look smaller because you're minimizing, but don't actually correspond to actual choice of edges. You can't actually use it to choose the edges you need. And this gap is called the integrality gap. And in order to maybe get a reasonable solution out of this, we need to take that linear solution and round it in order to do this. Okay. Okay. I think I got this wrong. I think the way to do this is by, the correct thing to do here is to just set it to be 1 as long as it's more than 0. So you will, Okay, we don't have time. Okay, so that's the correct thing here is to set this to 0 if it's 0, and to set to 1 if it's more than 0. What that effectively does is it gives you lots of extra edges, but you can show you don't get too many extra edges. But I'll talk about this next time. Okay. I posted a note on PR, so it turned out that we were all wrong, that it was not 26th, it was not 24th, it's 23rd that class is in. And 24th, which is a Wednesday, is the reading day. And I know I'm not supposed to put things on reading day, but my question for all of you is if we were to do the in-class exam on the reading day, and then I would give you the homework to be turned in on Sunday, the final part of the final to be turned on Sunday, that's one possibility. That's the only possibility that works within the current framework, because by Thursday, the final start, which means on Friday this room won't be available. Some other class will be doing the exam. So, again, I would like to know your thoughts on this. You can express them here, or you can put them in the comments out there. I just want to like to get the sense of the class and how people feel about this. Yes?
I don't get the date.
So okay, 26th is a Friday, 25th is a Thursday. Final exam starts on the 25th, which means 26th, this room is no longer available. 23rd is the last day of classes. 24th, which is a Wednesday, is the reading day. Right, so it's a break between the classes. It's sort of normally a day where you can get ready for the finals. Right? So one option is to do it, which is not entirely sort of kosher, but to do it on that reading day, on the 24th, in class. So you come to class and just do it here. That would be one part of the exam, and the other part would be a take home. That's the proposal on the table. So I just like to